For billions of years, galaxies drift through the universe carrying something hidden at their cores. Supermassive black holes. Not isolated objects, but gravitational anchors, millions or billions of times more massive than the Sun, quietly shaping the motion of entire galaxies. When galaxies collide, their stars rarely crash into each other. Their gas slowly mixes, their structures distort and stretch. But at the center, something unavoidable begins. Two supermassive black holes fall toward one another. At first, they orbit from a great distance, separated by thousands of light years, then hundreds, then less. They spiral inward over immense spans of time, releasing energy not as light, but as ripples in space-time itself. This process is slow, silent, and invisible to the eye, until the final moment. In this documentary, we follow that long descent toward the instant when two supermassive black holes finally merge. What happens to space and time? What kind of signal is released across the universe? And how these events reshape galaxies on the largest scales. Everything you're about to hear is based on modern astrophysics, gravitational wave science, and observations from the most advanced instruments ever built. If you enjoy long-form explorations like this, calm, accurate, and focused on the deepest structures of the universe, you can subscribe now to continue exploring these cosmic events whenever you return. Now, let's begin at the moment when two galaxies become one, and something far more extreme starts to happen at their cores. Long before two supermassive black holes ever meet, something much larger sets the process in motion: galaxies. Across the universe, galaxies are not fixed islands. They drift, pull on one another, and slowly reshape their surroundings through gravity. Over billions of years, this motion brings galaxies closer together, not in sudden crashes, but in gradual, inevitable encounters. When two galaxies begin to approach, the event is not violent in the way explosions are violent. The distances between stars are so vast that direct stellar collisions are rare. Instead, the galaxies pass through each other, their shapes stretching and distorting as gravity takes hold. Arms elongate, gas clouds compress. New stars may ignite where material is disturbed, but the most important change happens at the center. Almost every large galaxy contains a supermassive black hole at its core. These objects are not just heavy, they dominate the gravitational environment of the inner galaxy. They shape how stars orbit, they influence how gas moves, they anchor the galaxy's structure. When galaxies merge, their central black holes are carried along with them. At first, these black holes remain far apart, separated by thousands of light years. Each one continues to sit at the center of its original galactic core, surrounded by stars and dense clouds of gas. This stage can last hundreds of millions of years. The galaxies may already appear merged to an outside observer, their stars mixed into a single structure, but deep inside, the two black holes are still distant, each moving through the combined gravitational field of the newly forming galaxy. The journey towards merger is slow. Unlike stars or planets, black holes do not lose energy easily. They do not emit light. They do not experience friction in the usual sense. Something else must drain their orbital energy before they can fall together. That process is gravity itself. As each black hole moves through the dense environment of the galactic core, it interacts gravitationally with surrounding stars and gas. These interactions create a subtle effect known as dynamical friction. Stars passing near a black hole are pulled slightly off their original paths. Over time, these small deflections add up. The black hole transfers energy to the surrounding stars, causing them to drift outward while the black hole slowly loses momentum. This does not happen quickly. Millions of stars must be involved. Millions of interactions must occur. The timescale stretches across hundreds of millions to billions of years. But the direction is clear. The two supermassive black holes sink toward the center of the merged galaxy, drawn inward by the combined gravitational pull of everything around them. Eventually, they form a bound system. At this point, the two black holes are close enough that they begin orbiting each other directly. Astronomers call this stage a supermassive black hole binary. The separation may now be measured in light years or even fractions of a light year. On cosmic scales, this is extremely close. On human scales, it is still incomprehensibly vast. The environment around them becomes increasingly extreme. Gas clouds spiral inward, heating up as they fall. Intense radiation may be produced as matter accelerates toward the black holes. In some galaxies, this process creates active galactic nuclei, regions so bright they can outshine the entire galaxy. But light is still not the main story. The most important signal is invisible. As the two black holes orbit each other, they distort space and time. According to Einstein's theory of general relativity, accelerating massive objects produce gravitational waves, ripples in space-time that travel outward at the speed of light. At first, these waves are weak. The black holes are still relatively far apart. Their orbital speeds are modest by relativistic standards. The energy carried away by gravitational waves is small compared to the total energy of the system. But even this weak emission matters. Every ripple carries away energy and angular momentum. Slowly, imperceptibly, the orbit shrinks. The black holes spiral closer together. This stage can last a very long time, and for decades it puzzled astrophysicists. There was concern that black holes might stall before reaching the final merger, unable to lose enough energy once nearby stars and gas were depleted. This problem became known as the final parsec problem. Modern simulations suggest that in real galaxies, this stalling is unlikely to be permanent. Galaxies are messy systems. New stars pass through the center. Gas flows in irregular ways. The environment remains dynamic enough to continue draining energy from the binary. Eventually, gravity takes over completely. The distance between the black holes becomes so small that gravitational wave emission dominates all other effects. From this point forward, the merger is inevitable. The orbit accelerates. The black holes circle each other faster and faster, completing orbits in years, then days, then minutes. Space itself becomes violently distorted near the pair, though nothing resembling an explosion occurs. There is no surface, no collision in the conventional sense, no flash of light marking the moment. What happens instead is a deep rearrangement of space-time, but that final moment is still far ahead. Before the merger itself, the universe experiences something remarkable, a long, slow broadcast of gravitational information. The black hole binary becomes a lighthouse of space-time ripples, sending a signal that can travel across billions of light years. Unlike light, these waves pass through matter almost untouched. They carry a pristine record of the motion that created them. For the first time in human history, scientists have begun detecting such signals. Not yet from supermassive black holes, but from smaller black hole mergers. These detections confirm that the process is real, and they give us confidence that far larger mergers are happening throughout the universe. Somewhere right now, in distant galaxies, supermassive black hole pairs are spiraling inward. Their host galaxies may already look calm and settled. Stars orbit peacefully. From the outside, nothing appears unusual. But deep at the center, space-time itself is slowly tightening. This is not a rare event. Galaxies merge frequently over cosmic time. Every major galaxy is likely to have experienced multiple mergers. That means supermassive black hole mergers are a natural outcome of how the universe builds structure. Each merger reshapes the galaxy that follows. The final black hole will be more massive than either of its predecessors. Its spin will be altered. Its gravitational influence will extend farther than before. In some cases, the merged black hole may even receive a gravitational kick, moving slightly off-center before settling back into the core. This recoil happens when gravitational waves are emitted asymmetrically, carrying momentum away in one direction. Even this does not tear the galaxy apart. The galaxy adapts. Gravity reorganizes orbits. Gas flows adjust. Over time, the system finds a new balance. All of this begins long before the dramatic finale. Once two galaxies merge, once their central black holes are drawn together, there is no known mechanism that can permanently stop the process. It may take immense time. It may proceed quietly, but gravity does not forget. The universe is patient. In the next part, we will move closer to the final stages of the inspiral, where gravity waves dominate. Space-time becomes extreme, and the merger shifts from a slow cosmic dance to one of the most energetic events the universe can produce. Without light, without sound, and without warning. Once two supermassive black holes form a bound pair at the center of a merged galaxy, the universe enters a long, quiet phase that is easy to underestimate. From the outside, the galaxy may look stable. Its stars follow smooth orbits, its overall shape slowly relaxes into something familiar. There is no visible sign that something extraordinary is unfolding deep at its core. But at the center, the two black holes are locked in a gravitational relationship that cannot be undone. They orbit each other. At first, this orbit is wide. The black holes may be separated by distances comparable to the size of the solar system, or much larger. At these scales, their motion is slow, and the effects they produce are subtle. The merger is no longer a question of if, it is a question of how long. The main challenge is energy. For the black holes to fall closer together, they must lose orbital energy. They cannot collide directly, and they cannot shed energy by friction the way ordinary objects do. Instead, they rely on their environment and on the structure of space-time itself. In the early stages of the binary phase, the surrounding galaxy plays a crucial role. The region near the center of a galaxy is crowded. Stars move on complex paths, passing near the black holes again and again. Each close encounter slightly alters the star's orbit and slightly slows the black hole. This process continues relentlessly. Stars that pass too close may be flung outward at high speeds, carrying away energy. Others are captured and eventually consumed. Each interaction drains a small amount of orbital momentum from the black hole pair. Over millions of years, these tiny losses accumulate. The orbit tightens. The black holes draw closer. As they do, the environment around them changes. The number of stars available for interaction decreases. Many have already been scattered or consumed. Gas clouds may be heated or driven away by energetic activity near the core. The once rich environment begins to thin. This is where the merger process slows down. For a long time, astrophysicists worried that black holes might become stuck at this stage, unable to lose enough energy to continue inward. This theoretical concern became known as the final parsec problem, named after the approximate distance at which the process seemed to stall in simplified models. But real galaxies are not simplified systems. They are chaotic, asymmetric, and constantly evolving. New stars pass through the core, gas flows are irregular, the combined gravitational field of the galaxy is rarely smooth or static. These irregularities keep the process moving. The black holes continue to lose energy, even if slowly, until a new mechanism becomes dominant: gravitational waves. According to general relativity, any accelerating mass distorts space-time. When two massive objects orbit each other, they produce ripples that propagate outward at the speed of light. At large separations, the energy carried away by these waves is tiny, but as the black holes draw closer, the effect increases dramatically. The strength of gravitational wave emission depends strongly on distance. As separation decreases, the power radiated rises sharply. There comes a moment when gravitational waves take over completely. From this point forward, the surrounding galaxy becomes almost irrelevant to the fate of the pair. The black holes no longer need stars or gas to lose energy. Space-time itself does the work. The orbit begins to shrink more rapidly. The black holes circle each other faster and faster, completing more orbits in less time. Each orbit sends out a precise pattern of gravitational waves, encoding information about the masses, spins, and geometry of the system. If an observer could somehow listen to space-time, this signal would sound like a rising tone, a slow cosmic chirp growing higher and stronger as the merger approaches. But there is no sound, only motion and distortion. At this stage, the system becomes one of the most extreme environments in the universe. The gravity near each black hole is immense. Space and time are warped beyond anything experienced near stars or planets. Paths that would be straight elsewhere are bent sharply inward. Time flows differently close to the black holes than it does far away. Yet even now there is no flash of light announcing what is coming. Supermassive black hole mergers are not necessarily bright in the electromagnetic sense. They do not always produce dramatic bursts of radiation. Much of the energy involved is released in a form humans cannot see. Gravitational waves carry away vast amounts of energy, sometimes equivalent to the mass of millions of suns converted directly into space-time distortions. This energy does not heat the surroundings. It does not illuminate the galaxy. It passes through the universe almost unnoticed. Only instruments designed to detect changes smaller than an atomic nucleus can sense it. As the inspiral accelerates, the black holes approach a critical regime. Their velocities become a significant fraction of the speed of light. Their gravitational fields interact strongly. Simple approximations break down. Only the full equations of general relativity can describe what happens next. The system enters the final inspiral. The distance between the black holes shrinks rapidly. Orbits that once took years now take days, then hours, then minutes. Space near the pair becomes violently dynamic, constantly reshaped by their motion. Nothing can intervene. There is no external force strong enough to pull them apart. There is no stable orbit remaining. Gravity has closed the door behind them. This is the point of no return. From here, the merger will happen on a time scale measured not in millions of years, but in moments. The galaxy around them remains largely unaffected in the short term. Stars continue their slow motion. Light travels as it always has. From far away, nothing dramatic appears to be happening. But at the center, space-time is preparing for one of the most profound events allowed by physics. In the next part, we will move into the final seconds of the merger itself, when the two event horizons distort, touch, and become one, and when space-time rings with a signal that carries the unmistakable signature of a new black hole being born. This is where the slow spiral ends, and something irreversible takes its place. There is no warning when the final phase begins. No signal travels ahead of it. No light announces what is about to happen. No structure in the galaxy prepares itself. The two supermassive black holes have crossed a boundary where the future is no longer negotiable. They are no longer simply orbiting, they are falling together. At this stage, the distance between the black holes is measured not in astronomical units or light years, but in multiples of their own event horizons. Space near them is no longer gently curved. It is violently distorted, reshaped continuously by their motion. Time itself becomes uneven. Near each black hole, time slows dramatically relative to the outside universe. To a distant observer, processes near the event horizon appear frozen, but from within the system, everything accelerates. The inspiral reaches its final seconds. The black holes orbit each other at a significant fraction of the speed of light. Their gravitational fields interact in complex, non-linear ways that cannot be described by simple equations. This is the regime where Einstein's theory of general relativity is tested to its limits. Space and time are no longer a passive stage, they are active participants. As the black holes spiral inward, space-time is dragged, twisted, and stretched. The region around them becomes a dynamic landscape of shifting curvature, changing from moment to moment. Gravitational waves now dominate everything. They are no longer faint ripples. They are powerful, coherent distortions propagating outward in all directions. Each wave carries precise information about the system, its mass, its geometry, and its motion. The frequency of these waves rises rapidly. The signal grows stronger. The chirp reaches its peak. Then the horizons touch. This moment is not a collision in the usual sense. Black holes do not have solid surfaces. There is nothing to smash together. Instead, what merges are regions of space-time from which nothing can escape. The two event horizons deform as they approach, stretching toward each other like droplets of liquid under gravity. In simulations, they briefly form a connected shape before settling into a single larger horizon. This is the instant of merger. From the outside, there is no flash, no explosion, no burst of light. The most dramatic event is invisible. The new black hole is born already hidden behind its own horizon. Inside that boundary, physics enters a regime we cannot observe directly. General relativity predicts the formation of a single central singularity, but what actually occurs remains unknown. Our theories cannot describe conditions beyond this point with certainty. What we can describe is what happens outside. The newly formed black hole is not immediately stable, it is distorted, misshapen, spinning. The merger leaves it vibrating, like a struck bell made of space-time itself. These vibrations are called ringdown. They produce a final series of gravitational waves, each with a characteristic frequency and decay time. Together they encode the mass and spin of the newborn black hole. This signal is extraordinarily clean. Unlike light, which can be scattered or absorbed, gravitational waves carry their information almost unchanged across the universe. By measuring the ringdown, scientists can confirm whether the final object behaves exactly like a black hole predicted by general relativity. So far, every observation agrees. The universe follows the equations precisely. The energy released in this brief moment is staggering. For a supermassive black hole merger, the total energy emitted as gravitational waves can exceed the combined luminosity of all the stars in the observable universe, released not as light, but as distortions in space-time. And yet this release lasts only minutes or hours. Then it is over. The waves race outward at the speed of light, passing through galaxies, stars, planets, and empty space without resistance. They stretch and compress space-time by amounts far smaller than an atomic nucleus, but over distances measured in billions of light-years. If detected, they arrive long after the merger itself is finished. The galaxy that hosted the event may show little immediate change. Stars continue to orbit. Gas clouds drift. On large scales, the structure remains intact, but deep at the center, the gravitational anchor has changed. The merged black hole is more massive than either of its predecessors. Its spin may be faster or slower depending on the alignment of the original pair. Its orientation may be tilted relative to the galaxy. In some cases, the merger produces a recoil. If the gravitational waves were emitted asymmetrically, conservation of momentum demands that the black hole receives a kick in the opposite direction. For supermassive black holes, this kick can reach thousands of kilometers per second. Most galaxies can hold on to their central black hole despite this jolt, but in smaller galaxies, the merged black hole may be displaced from the center or even ejected entirely, leaving the galaxy without its original core. This does not destroy the galaxy, it adapts. Over time, stars rearrange. New structures form, gravity finds a new balance, the merger is complete. But its consequences unfold over millions of years. The gravitational waves continue travelling outward, crossing the universe long after the local environment has settled. They carry with them a permanent record of the event, a signature that cannot be erased. In the distant future, these waves will pass through regions of space that no longer contain stars, galaxies, or even matter in any familiar form. They will continue on, unchanged, until the structure of space-time itself no longer allows their propagation. From the perspective of physics, the merger is not dramatic. It is precise, it is inevitable. It is one of the purest expressions of gravity's role in shaping the universe. Two regions of space-time fall together, merge, and settle into a new configuration that obeys the same rules as everything else. No announcement is made, no preference is expressed. The universe does not mark the moment, but in that silent instant something fundamental has changed. Two separate gravitational histories have become one. In the next part, we will step back from the moment itself and explore how these mergers shape the long-term evolution of galaxies, influence cosmic structure, and quietly define the architecture of the universe on the largest scales. Because while the merger is brief, its influence is anything but. Once the gravitational waves have passed and the space-time vibrations have faded, the universe does not pause to acknowledge what has happened. There is no aftershock in the ordinary sense, no visible scar left behind, no sudden transformation that announces the event. From a distance, the galaxy appears much as it did before. Stars continue their slow orbits, gas clouds drift through interstellar space, light travels outward, uninterrupted. But deep at the center, the galaxy is no longer the same system. The merger of two supermassive black holes fundamentally alters the gravitational core around which everything else is organized. The new black hole is heavier than either of its predecessors. Its gravitational influence extends farther into the galaxy. Orbits that were once stable may shift slightly. Paths that were once circular may become elongated. Over long timescales, these small changes accumulate. Galaxies evolve quietly. The most immediate effect of the merger is the settling of the new black hole into equilibrium. After the violent distortion of space-time during the merger, the black hole sheds any remaining asymmetry through its final ring-down. Once this is complete, it becomes a remarkably simple object, defined only by its mass, spin, and charge. In astrophysical reality, charge is negligible. What remains is mass and rotation. This simplicity hides enormous influence. The central black hole does not act alone. It interacts with the surrounding environment in subtle but persistent ways. Gas flowing toward the center responds to the new gravitational field. Stars passing nearby experience slightly altered trajectories. The density of the galactic core adjusts over time. In some galaxies, this change triggers renewed activity. Gas may spiral inward more efficiently, heating up as it accelerates. Radiation is produced as matter approaches the event horizon. The galaxy may briefly become active again, its core shining as an active galactic nucleus or even a quasar. This activity is not caused by the merger directly, it is enabled by it. The merger rearranges the central gravitational landscape, making it easier for matter to fall inward. In this way, black hole mergers can regulate when galaxies appear bright or quiet over cosmic time. But this activity does not last forever. As gas is consumed or expelled, the galaxy settles into a calmer state. The black hole becomes quiescent again, exerting its influence silently. Over millions of years, the merger's most visible signatures fade. What remains is structural. The galaxy now has a different center. One of the most profound consequences of supermassive black hole mergers is their role in shaping galactic growth. Observations show a tight relationship between the mass of a galaxy's central black hole and the properties of its surrounding stars. This suggests that black holes and galaxies evolve together, influencing each other across time. Mergers are a key part of that relationship. Each merger increases the mass of the central black hole. As galaxies merge repeatedly across cosmic history, their black holes grow step by step. This growth affects how gas cools, how stars form, and how energy is distributed throughout the galaxy. In this sense, black hole mergers act as a kind of cosmic regulator. They do not control galaxies directly, they set conditions. By altering the flow of matter and energy, they influence what kinds of structures can form next. Another consequence of the merger is angular momentum. The spin of the merged black hole may be dramatically different from the spins of the original pair. Depending on their alignment, the final spin can be faster, slower, or tilted relative to the galaxy's rotation. This misalignment matters. Jets of high-energy particles, when they form, are launched along the black hole's spin axis. If that axis changes, the direction of these jets changes as well. Over time, this can carve different paths through the surrounding gas, affecting star formation on large scales. Once again, these effects are slow. There is no instant transformation. Galaxies are patient systems. In rare cases, the recoil from the merger plays a larger role. If the merged black hole receives a strong gravitational kick, it may oscillate around the galaxy's center for millions of years. During this time, the galaxy lacks a stable central anchor. The core becomes less dense. Stellar orbits become more chaotic, In extreme cases, the black hole may be ejected entirely. Such galaxies are rare, but they reveal something important. Galaxies can survive without a central supermassive black hole. They do not collapse, they do not dissolve, they simply evolve differently. Gravity reorganizes itself around the remaining mass of. This reinforces a broader truth about the universe. Even the most extreme events do not produce fragility, they produce adaptation. On the largest scales, supermassive black hole mergers contribute to the structure of the universe in a way that is almost invisible. They help determine how galaxies grow, they influence when stars form, they shape the flow of matter across cosmic time, yet they do so without spectacle. There is no universal marker of a merger's completion. No cosmic signal says this galaxy has changed. Only long-term observation reveals the difference. From the perspective of space-time, the merger is already finished. The gravitational waves have passed. The new geometry has settled. The universe has moved on. But the consequences continue to unfold quietly. This is a recurring pattern in cosmic evolution. The most energetic events often leave the most subtle long-term traces. Supermassive black hole mergers are among the most powerful processes allowed by physics, and yet their legacy is not chaos, it is structure. They help explain why galaxies look the way they do today, why their centers are dense, why their growth slows over time, why massive galaxies tend to be quiet while smaller ones remain active longer. None of this requires intention. It emerges from gravity following its rules. As time passes, galaxies continue to merge. Each merger brings new black holes together. Each new pair begins the long journey toward inspiral, merger, and settlement. The universe repeats this process again and again, not because it aims to, but because gravity has no alternative. In the next part, we will move beyond individual galaxies and examine what these mergers mean for the universe as a whole, how they contribute to a background of gravitational waves, how they encode information about cosmic history, and how they allow us to study space-time itself in ways that light never could. But its echo continues, quietly shaping everything that follows. Once the merger is complete and the galaxy has begun to settle into its new structure, it may seem as though the event has fully passed into the past. The black hole has stabilized. The surrounding stars have adjusted. The visible universe moves on, apparently unchanged. But, in another sense, the merger is still happening, not locally, not visibly, but across the universe itself. Every supermassive black hole merger releases a vast amount of energy in the form of gravitational waves. These waves do not stop when they leave the galaxy. They do not dissipate quickly. They do not fade in the way light does when it spreads out. They continue traveling across billions of light years, across empty space, across epochs of cosmic history. Each merger sends out a signal that becomes part of a larger, invisible structure known as the gravitational wave background. This background is not a single event. It is the accumulated imprint of countless mergers across the universe's history. Every time two supermassive black holes merge, their waves add to this cosmic record, overlapping and blending with waves from other mergers past and future. The result is a faint, persistent hum in space-time itself. Unlike light, which can be absorbed, scattered, or blocked, gravitational waves move almost unhindered. They pass through galaxies, stars, planets, and even black holes without losing their identity. Nothing shields the universe from them. This makes gravitational waves unique. They carry information that survives almost unchanged from the moment of emission. In a sense, they are the universe's most reliable messengers, preserving the details of events that may have occurred billions of years ago. For supermassive black hole mergers, this background is especially important. These mergers are rare compared to smaller black hole collisions, but they are enormously powerful. Their gravitational waves have long wavelengths stretching over light years, and low frequencies that cannot be detected by ground-based observatories. Instead, scientists search for them in an indirect way, They use the universe itself as a detector. By monitoring the precise timing of rapidly spinning neutron stars known as pulsars, astronomers can detect tiny distortions in space-time caused by passing gravitational waves. As waves from distant mergers pass between Earth and these pulsars, they slightly alter the arrival times of the pulses. Over years of observation, these deviations reveal a pattern, a background, a quiet cosmic signal produced not by one merger but by many. This background tells a story about the universe that light alone cannot. It reveals how often galaxies merge, how massive their central black holes are, how structure has grown over cosmic time. In this way, every supermassive black hole merger becomes part of a larger narrative written directly into space-time, and this narrative does not fade. Even as galaxies evolve and stars die, the gravitational waves continue their journey. Long after the local effects of a merger are gone, its signal is still out there, stretching space and time ever so slightly as it passes through new regions of the universe. In the far future, when the universe is darker and quieter, these waves will still exist, unless space-time itself changes in a way that prevents their propagation. This persistence raises a subtle point. Supermassive black hole mergers are not isolated events. They are part of a continuous process that links the formation of structure in the early universe to its long-term evolution. Each merger encodes information about the conditions under which it occurred, the masses involved, the spins, the geometry of space-time at that moment. By studying the gravitational wave background, scientists are not just detecting distant events, they are reading a cumulative record of how the universe built itself. This is something light cannot provide. Light tells us about hot, luminous matter. It reveals stars, gas, and energetic processes. But light is limited. It can be absorbed, it can be scattered, it can be blocked by dust. Gravitational waves ignore these obstacles. They reveal the dark processes, the mergers, the collapses, the movements of massive objects that may produce little or no light at all. Supermassive black hole mergers are among the clearest examples of this. Many such mergers produce no obvious electromagnetic signature. The galaxies involved may appear calm, no bright flare may announce what has occurred. And yet, space-time itself carries the evidence. This changes how we think about observation. The universe is no longer something we only see. It is something we listen to, not with sound, but with precise measurements of space and time. As detection techniques improve, scientists expect to observe individual supermassive black hole mergers directly through their gravitational waves. Future observatories in space will be able to detect the inspiral and merger of these giants in exquisite detail. When that happens, each detection will provide a direct test of general relativity in the most extreme conditions imaginable. Do black holes behave exactly as Einstein predicted? Does space-time respond precisely as our equations describe? Are there subtle deviations that hint at new physics? So far, every observation has confirmed the theory. The universe is consistent, but the potential for discovery remains. Beyond testing gravity, these observations will deepen our understanding of cosmic history. They will reveal how quickly galaxies assembled, how often mergers occurred in the early universe, how black holes grew from relatively small seeds into the enormous objects we see today. In this sense, supermassive black hole mergers connect the smallest scales of space-time distortion to the larger scales of cosmic structure. They are bridges between local events and universal patterns, and this connection persists long after the merger itself is finished. There is something almost paradoxical about this. The most violent gravitational events leave the most subtle long-term traces. No explosion marks their passage. No debris field remains. Instead, what lingers is a barely detectable change in the fabric of space-time itself, a whisper rather than a shout. This fits a broader pattern in the universe. The most fundamental processes are often the quietest. Gravity does not announce itself loudly. Space-time does not advertise its distortions. The universe records its history not in spectacle but in structure. Supermassive black hole mergers are extreme expressions of this principle. They reshape galaxies, they send signals across the universe, they encode information that may outlast stars themselves, and yet they do so without fanfare. As cosmic time continues, mergers accumulate. The gravitational wave background grows richer, the universe's space-time memory becomes more complex. Each new merger adds another layer to a record that stretches across billions of years. In the far future, long after galaxies have faded and stars have died, these waves may be among the last remaining traces of the universe's dynamic past, unless space-time itself changes. This possibility leads to deeper questions. What happens to gravitational waves in an ever-expanding universe? Do they stretch and weaken indefinitely? Do they eventually lose meaning as distances grow beyond causal contact? Current physics suggests that gravitational waves, like light, are stretched by cosmic expansion. Their wavelengths grow longer, their energy becomes more diffuse. Over immense timescales, they fade into the background. But fade does not mean vanish. Their information is not erased in the ordinary sense. It becomes increasingly difficult to access, increasingly diluted by the vastness of space. In this way, the universe slowly forgets. Not abruptly, not violently, but gradually. Supermassive black hole mergers contribute to this slow forgetting. They add to the record even as expansion works to spread that record ever thinner. This tension between events that encode information and a universe that dilutes it is one of the defining features of cosmic evolution. It is not unique to black hole mergers. It applies to everything. But mergers sit at an extreme point in this balance. They are among the last major events the universe can produce at large scales. As the universe ages and structure formation slows, galaxy mergers become rarer. Supermassive black hole mergers follow the same trend. Eventually, the universe enters an era where new mergers are unlikely. Galaxies drift too far apart, matter becomes too diffuse, gravity loses its ability to assemble new large structures. At that point, the gravitational wave background becomes a fossil, a record of a time when the universe was active, dynamic, and capable of dramatic change. Supermassive black hole mergers will belong to the deep past, but their echoes will still be woven into space-time itself. In the next part, we will step beyond even this background and consider the far future, when mergers cease, when space-time quiets, and when the universe approaches a state where even gravity's grandest events are no longer possible. The silence that follows is not sudden, it is earned, and it tells us as much about the universe as the mergers themselves ever did. There comes a time in the universe's history when even the largest structures lose their ability to interact in meaningful ways. This transition does not happen abruptly. There is no boundary marked in space or time. Instead, it unfolds gradually, as expansion stretches distances and drains gravity of its power to assemble new systems. Supermassive black hole mergers belong to an era when the universe was still capable of gathering matter on the largest scales. That era does not last forever. As cosmic expansion accelerates, driven by dark energy, galaxies begin to drift apart faster than gravity can pull them together. Groups of galaxies that are bound today will remain bound, but beyond those local regions, separation becomes permanent. The universe fragments into isolated islands. Within each island, the remaining galaxies may still interact. Their stars may orbit, their central black holes may merge, but the number of opportunities steadily decreases. Galaxy mergers become rarer. Without mergers, new supermassive black hole pairs cannot form. This marks a profound shift in cosmic behavior. For billions of years, structure formation was the dominant theme of the universe. Matter flowed inward. Gravity assembled increasingly complex systems. Galaxies grew through collisions and mergers. Black holes gained mass by consuming matter and by merging with one another. Expansion did not prevent this process at first. Gravity was strong enough, distances were small enough, and matter was dense enough for structure to thrive. But expansion never stopped. As space stretched, matter became more dilute. The average distance between galaxies increased. The time required for gravity to overcome that distance grew longer. Eventually, gravity lost the race. Not everywhere at once, but globally. When that happens, the universe enters a quieter phase. Not because gravity disappears, but because it no longer has the opportunity to create new large-scale interactions. The last supermassive black hole mergers occur during this transitional era. These final mergers may happen trillions of years from now, inside the largest gravitationally bound structures that still exist. Galaxy clusters will continue to evolve internally even as the rest of the universe drifts away beyond reach. Within these clusters, black holes will continue their slow inspirals. Gravitational waves will still be emitted. Space and time will still be distorted by their motion. But once these clusters exhaust their supply of merging galaxies, the process ends. No new black hole binaries form. The universe does not replace them. This is not because black holes lose their ability to merge. It is because the universe no longer provides the conditions required to bring them together. This distinction is important. Physics does not prohibit mergers. It simply stops enabling them. The remaining supermassive black holes settle into isolation. Each one sits at the center of its host galaxy, which itself becomes increasingly isolated from all others. Over immense spans of time, stars burn out. Gas is depleted or expelled. The galaxy grows dim. The black hole remains. It is now a relic of an earlier cosmic era. Without fresh matter falling in, the black hole becomes quiescent. It emits little radiation. Its presence is known only through its gravitational influence on the remaining stars. No dramatic events announce this transition. The universe does not signal that it has entered a new phase. It simply changes what it allows. This shift has consequences for space-time itself. With fewer mergers, the gravitational wave background begins to thin. New contributions slow, the universe's space-time memory becomes dominated by older events. Over vast timescales, expansion stretches these waves. Their wavelengths grow, their energy spreads thin. Eventually they blend into the fabric of space-time, no longer distinguishable as signals. This does not mean the waves are destroyed, it means their information becomes inaccessible. The universe forgets, not through erasure, but through dilution. As supermassive black hole mergers cease, one of the universe's most powerful mechanisms for reshaping galaxies disappears. The architecture of cosmic structure becomes fixed. Galaxies continue to evolve internally, but their large-scale relationships are frozen. This has a subtle effect on the future of complexity. Without mergers, galaxies no longer receive fresh gas from interactions. Star formation slows and eventually stops. The universe grows darker and more static. The era of dramatic gravitational events comes to an end, not because the universe collapses, but because it runs out of opportunities. This marks a turning point. Up until now, gravity has been a creative force, assembling matter into ever larger structures, from particles to atoms, from atoms to stars, from stars to galaxies, from galaxies to clusters. Supermassive black hole mergers represent the peak of this process. They are gravity acting on the largest masses over the largest distances. When these mergers stop, gravity's role changes. It becomes conservative rather than creative. It maintains what already exists instead of building something new. This transition is one of the least dramatic yet most profound changes in the universe's history. There is no catastrophe, no collapse, no end, just a gradual narrowing of possibilities. The universe still contains enormous energy. It still contains matter. It still contains space-time governed by the same laws, but it no longer arranges these ingredients into new large-scale patterns. The cosmic dance slows. Eventually it stops adding new steps. Supermassive black hole mergers were among the last truly global events in the universe. They linked distant regions through gravitational waves. They reshaped entire galaxies. They left marks that could be detected across cosmic distances. When they cease, the universe becomes more local. Events still happen, but they happen in isolation. Each gravitational island evolves independently, unaware of what occurs beyond its shrinking horizon. This isolation is not hostile, it is structural. It arises naturally from the expansion of space. As time continues, even within these islands, activity declines. Stars exhaust their fuel, stellar remnants cool. Matter becomes locked into compact objects or scattered thinly through space. The black holes persist, but they no longer grow, they wait. This waiting is not anticipation, it is simply the absence of change. Gravity has done all it can at this scale. The universe has moved beyond the era where it could bring giants together. In the next part, we will follow these remaining supermassive black holes forward in time into an era where even they begin to change, not through mergers, but through the slow, inevitable effects of time itself. The universe does not end its story loudly. It lets its most dramatic chapters quietly close. After the era of mergers ends, the universe enters a phase defined not by violence or transformation, but by separation. The great interactions that once shaped galaxies and rewrote space-time are no longer possible. Expansion has carried most structures beyond each other's reach, and gravity's role as a cosmic architect has largely concluded. What remains are isolated systems. Within each gravitational island, galaxies continue to exist, but they no longer encounter new partners. Their shapes are fixed. Their populations slowly age. Star formation declines as available gas is exhausted or locked away in long-lived remnants. At the centers of these galaxies sit supermassive black holes. They are no longer growing through mergers. They are no longer fed by large inflows of fresh material. Their environment becomes quiet, predictable, and increasingly empty. For the black holes themselves, nothing dramatic changes at first. A black hole does not require activity to exist. It does not decay through ordinary processes. It does not erode simply because matter is scarce. As long as space-time behaves according to the laws we understand, a black hole can persist indefinitely without interacting with its surroundings. From the outside, these black holes appear almost eternal. But time in the universe is not finished with them. As the galaxies around them grow dimmer, the black holes become the most massive and influential objects still active in their regions. Their gravitational pull continues to shape stellar orbits, even as the number of stars decreases. Occasionally, a star passes too close. In earlier eras, such encounters might have been frequent, feeding the black hole and producing bright flares of radiation. Now, they are rare. The galaxy's core is sparsely populated. Stellar orbits have stabilized. Most stars that could have fallen in already did so long ago. When a star is captured in this late era, it is an isolated event, a brief localized release of energy that quickly fades. There is no ongoing activity to sustain brightness. The black hole returns to silence. Over immense timescales, galaxies themselves change character. Without star formation, they become collections of stellar remnants, white dwarfs, neutron stars, and black holes. Light becomes scarce, motion slows. The galaxy cools toward equilibrium. The supermassive black hole remains at the center, unchanged in appearance but increasingly dominant by comparison. This dominance, however, is deceptive. Gravity alone does not create change. It requires something to act upon. With little matter left to move, even the strongest gravitational field becomes static. The black hole's influence is absolute but uneventful. In this era, the universe begins to resemble a museum of its own past. Structures persist, but nothing new is built. The memory of violent mergers exists only in the form of mass distribution and faint gravitational imprints stretched thin by expansion. Time continues to pass, and with time comes a process that even black holes cannot avoid. Hawking radiation. According to quantum theory, black holes are not perfectly black. At their event horizons, quantum effects allow a slow leakage of energy in the form of radiation. For stellar mass black holes, this process is already unimaginably slow. For supermassive black holes, it is almost inconceivably slower. A black hole with the mass of millions or billions of suns has a temperature far colder than the cosmic background radiation for most of the universe's history. As long as the universe remains warm by comparison, the black hole absorbs more energy than it emits. But the universe does not remain warm forever. As expansion continues, the background temperature drops. Eventually, after timescales vastly exceeding the current age of the universe, the cosmic background becomes colder than even the coldest supermassive black hole. Only then does Hawking radiation begin to dominate. At first, the effect is negligible. The mass loss is so small that it would take longer than trillions of years to notice any difference. The black hole remains, for all practical purposes, unchanged. But physics is patient. Given enough time, even the slowest process becomes decisive. The black hole begins to lose mass, not through dramatic evaporation, not through collapse, but through an unimaginably slow trickle of energy escaping its gravitational grip. This marks a new kind of evolution. For the first time since their formation, supermassive black holes begin to shrink. The universe is now in an era where the largest objects are not growing, not merging, not interacting, but gradually dissolving. This process does not depend on environment. It does not require matter or radiation nearby. It is intrinsic to the nature of black holes themselves. Each black hole follows the same fate, no exceptions. As mass decreases, the black hole's temperature rises. Radiation increases. The process accelerates, but only at the very end. For most of its existence, the black hole remains almost unchanged. From an external perspective, this era is defined by stillness. Galaxies are dark, stars are gone, mergers are no longer possible. The universe contains enormous masses but little activity. The isolation is complete. Each supermassive black hole exists alone in its region of space-time, slowly losing mass unnoticed and unobserved. There is no signal announcing this transition, no moment when the universe acknowledges that its largest structures have entered their final phase. It simply happens. In earlier eras, black holes were engines of change. They regulated galaxies, powered quasars, and shaped cosmic structure. Now they are relics, following a slow, inevitable trajectory toward disappearance. This does not mark the end of gravity. Gravity remains a fundamental interaction. It continues to govern motion and shape space-time, but its role as a creative force has ended. There is nothing left to assemble. The universe has exhausted its capacity for large-scale construction. What remains is maintenance followed by decay. In the next part, we will move forward into the era when even these isolated giants reach the final stages of their existence, when Hawking radiation becomes dominant, and when the universe loses the last objects capable of shaping space-time on grand scales. The age of mergers is long over, the age of isolation has begun, and time, unhurried and indifferent, continues to pass. For most of cosmic history, black holes were the closest thing the universe had to permanence. They survived the deaths of stars, the collapse of galaxies, and the end of structure formation itself. Long after light faded and motion slowed, they remained silent, massive, and seemingly eternal. But eternity was never promised. The isolation of the universe eventually creates the conditions for a subtle but irreversible change. As expansion continues and energy spreads thinner across space, the background temperature of the universe keeps dropping. Radiation becomes weaker, particles become rarer. The universe cools toward an extreme, nearly absolute calm. This cooling matters. For most of their existence, supermassive black holes are colder than almost nothing else, but not colder than the universe itself. They absorb more energy from their surroundings than they emit. This balance keeps them stable. Eventually, that balance breaks. After unimaginable spans of time, far beyond the lifespan of stars, galaxies, and even stellar remnants, the universe becomes colder than the black holes. At that moment, the direction of energy flow reverses. Hawking radiation takes over. This radiation does not erupt from the black hole in a burst. It seeps out, particle by particle, from the quantum boundary near the event horizon. The process is so slow that it defies intuition. A supermassive black hole can persist for timescales measured in 10 circumflex 90 to 10 circumflex 100 years or more, depending on its mass. For almost all of that time, nothing seems to change. The black hole remains dark, its gravitational pull remains strong, its presence continues to shape the sparse remnants of its galaxy. But beneath this apparent stillness, mass is being lost. Each emitted particle carries away a tiny fraction of the black hole's energy. With each loss, the black hole becomes slightly smaller. The event horizon shrinks. The temperature rises imperceptibly. There is no stable endpoint. The process cannot stop once it begins. Unlike mergers, which depend on the universe providing opportunities, Hawking radiation is intrinsic. It does not require matter, radiation, or interaction. It is built into the structure of space-time and quantum fields themselves. Every black hole is subject to it. This marks the final era in which black holes meaningfully evolve. As time passes, the universe becomes increasingly simple. Particles decay. Matter breaks down into lighter constituents. Even protons may eventually decay if certain theories are correct. Structures dissolve. Against this backdrop of simplification, black holes stand out, not as creators, but as reservoirs of mass and energy slowly leaking into nothing. The evaporation process accelerates near the end. For most of a black hole's life, mass loss is negligible, but as mass decreases, temperature increases and radiation becomes more intense. The final phase is brief compared to the black hole's total lifespan. Yet even this final phase is not dramatic in a familiar sense. There is no explosion that lights up the universe, there is no shockwave tearing through space, there is no witness to observe it. The universe is too empty by then. When the last supermassive black holes reach the end of their evaporation, the energy they release spreads into a universe so vast and dilute that it has no noticeable effect. The black hole simply ceases to exist. What remains is not a hole. It is not a scar, it is just space-time, slightly rearranged, continuing its expansion. This disappearance marks a profound milestone. Black holes were the last objects capable of significantly warping space-time on large scales. When they are gone, the universe loses its most extreme gravitational features. Curvature becomes gentle everywhere. No region of space contains an event horizon. No point traps light indefinitely. The geometry of the universe becomes smooth, uniform, and nearly featureless. This is not emptiness in the absolute sense. Particles still exist. Radiation still exists, quantum fields still fill space. But nothing dominates, nothing organizes matter into large structures. Nothing creates gradients strong enough to drive dramatic change. The universe enters a phase sometimes described as the dark era, but even that term suggests more activity than actually remains. Darkness implies contrast. There is little left to contrast against. Time continues, but its meaning becomes ambiguous. Without processes to mark its passage, no stars forming or dying, no mergers, no large-scale motion, time loses its physical anchors. It still exists mathematically, but it no longer corresponds to change in any familiar way. Events still happen, but they happen slowly, sparsely, and without connection. The evaporation of black holes removes one of the last mechanisms by which the universe could concentrate energy. From this point onward, energy spreads ever thinner, approaching uniformity. This is the universe approaching thermodynamic equilibrium, not a sudden heat death, but a gradual settling into sameness. There is no final moment when everything stops. There is no instant when the universe declares itself finished. Instead, change becomes so rare and so small that it loses significance. In earlier eras, supermassive black hole mergers linked distant regions of the universe through gravitational waves. Those waves carried information across cosmic distances, preserving a memory of dramatic events. Now, there are no new waves. The old ones are stretched beyond recognition by expansion. Their wavelengths exceed the size of observable regions. Their energy becomes negligible. Space-time grows quiet. It emerges naturally. The laws of physics have not changed. They simply have nothing left to act upon in dramatic ways. The universe has run out of contrast. This is not a failure of physics. It is its completion. The processes that once drove complexity have done their work. The conditions that allowed structure to form are no longer present. The universe transitions into a regime governed by the same rules but producing different outcomes. Minimal outcomes, uniform outcomes. From a certain perspective, this is the most stable state the universe can reach. No gradients to erase, no energy to redistribute, no structure to dismantle. Just continued expansion and gradual dilution. Black holes were among the last holdouts against this fate. Their immense gravity resisted uniformity for longer than anything else. Their evaporation marks the final surrender of concentrated structure. After this, the universe contains no objects that meaningfully stand out. Only fields, only particles, only space and time. This does not mean the universe is empty in the philosophical sense. It means it is complete in the physical sense. Nothing is trying to happen. Nothing is prevented from happening. Everything that can occur does so at an infinitesimal rate. In the next part, we will move even farther forward into a regime where the distinction between something and nothing becomes blurred, where quantum effects dominate an otherwise featureless cosmos, and where the universe exists not as a stage for events, but as a quiet, persistent condition. The age of black holes is over. The universe does not notice. It simply continues. After the last black holes have faded, the universe enters a state that is difficult to describe, not because it is complex, but because it is almost entirely without structure. For the first time since the earliest moments after the Big Bang, there are no dominant objects left, no stars, no galaxies, no black holes. What remains is a universe filled with an extremely thin distribution of particles and radiation stretched across an ever-expanding volume of space. The density of energy approaches zero. Differences between regions become vanishingly small. This is not emptiness in the absolute sense. Quantum fields still exist. Space itself still exists. Time still passes according to the equations of physics. But the universe no longer organizes itself into events that matter on large scales. In earlier eras, events were defined by contrast. A star igniting against darkness, a galaxy colliding with another, a black hole merging and reshaping space-time. Each of these required differences in energy, density, and motion. They required gradients for physics to act upon. Now, those gradients are gone. Energy is spread almost perfectly evenly. Particles are so far apart that interactions are exceedingly rare. Radiation has been stretched to wavelengths larger than any meaningful reference scale. Change has not stopped. It has become irrelevant. In this era, the universe approaches a state known as maximum entropy. This does not mean disorder in the everyday sense. It means that energy is distributed as uniformly as possible, leaving no available energy gradients to drive work or structure. Nothing is trying to happen anymore. Earlier, gravity pulled matter together. Thermodynamics pushed energy outward. These competing tendencies created structure, motion, and complexity. Now both have reached their limits. Gravity has nothing left to assemble. Thermodynamics has nothing left to even out. The universe becomes static in practice, even if not in principle. Time continues, but it no longer leaves marks. Without processes to measure it against, time loses its operational meaning. There are no clocks, no cycles, no repeating phenomena. The equations still allow time to exist as a dimension. But physically, nothing distinguishes one moment from the next. Moments blend into one another. The distinction between now and later becomes arbitrary. This is one of the strangest consequences of the far future. Time does not end, but it becomes empty. This emptiness extends to causality. In earlier eras, causes led to effects that could be observed, measured, and connected. In the late universe, interactions are so sparse that cause and effect chains are nearly non-existent. A particle may drift for trillions of years without encountering another. A quantum fluctuation may occur and vanish without influencing anything else. Events become isolated, disconnected, and inconsequential. The universe still obeys physical laws, but those laws rarely have the opportunity to produce outcomes of interest. This is not a collapse, it is not destruction. It is the exhaustion of possibility. The universe has explored nearly all the configurations that matter can meaningfully take under its laws. What remains are repetitions, trivial variations, and fluctuations too small to matter on any scale. Even quantum effects, which once introduced uncertainty and richness, lose their significance. Quantum fluctuations still occur, but without structure to amplify them, they remain microscopic. They do not seed new galaxies. They do not trigger large-scale change. They flicker and fade in isolation. The universe becomes dominated by vacuum energy and quantum fields in their lowest energy states. This raises a subtle question. Is this universe alive in any meaningful sense? From a physical perspective, it is functioning exactly as its laws dictate. Nothing is broken, nothing has failed. From an experiential perspective, there is nothing left to experience. There are no observers, no memory, no record. The universe is no longer a stage for stories. It is simply a condition. In this regime, the concept of end loses its usual meaning. An ending implies a final event, a last change, a moment of closure. But there is no such moment here. There is no final collapse. No ultimate silence that follows noise. No boundary between before and after. The universe does not stop. It settles. This settling is asymptotic. The universe approaches a state but never quite reaches a perfect endpoint. Change continues to occur, but at such a low rate and with such minimal consequence that it effectively disappears. This is sometimes described as the heat death of the universe, but that phrase can be misleading. It suggests an abrupt or dramatic transition. In reality, it is more like a long fading where contrasts gradually wash out until nothing stands apart. In this future, even information loses meaning. Information requires distinguishable states. It requires differences that can be encoded, stored, and transmitted. In a nearly uniform universe, distinguishable states become rare. Information still exists in principle, but there is no mechanism to preserve or utilize it. Memory disappears not through destruction but through dilution. This has an unsettling implication. Everything that ever happened, the formation of stars, the rise of galaxies, the mergers of black holes, has no lasting physical consequence at this stage. The universe does not remember its past, not because it erases it, but because there is no structure left that could contain that memory. This does not negate the past. It simply removes its influence. From a cosmic perspective, the universe has completed its dynamic phase. It has transitioned from becoming to being. This raises the deepest question of all. If nothing meaningful happens anymore, is the universe still doing anything? Physics answers yes. The equations continue to operate. Space expands. Quantum fields fluctuate. Particles drift. But these processes no longer produce novelty. They do not lead to new structures. They do not open new possibilities. The universe has reached a condition where the future contains nothing qualitatively different from the present. In this sense, the universe has reached equilibrium not just thermodynamically, but structurally. This is not a flaw in the laws of physics. It is their natural outcome. The same rules that allowed complexity to arise also guarantee that it cannot persist forever. This is the price of consistency. A universe that allows structure must also allow its dissolution. The transition to this final regime is not violent, it is not tragic. It is indifferent. The universe does not mourn the loss of activity. It does not value motion over stillness. It simply follows its rules to their conclusion. In earlier eras, black hole mergers represented the most extreme expressions of gravity. They bent space-time, reshaped galaxies, and sent signals across cosmic distances. Now, even those echoes are gone. Space-time is calm, uniform, quiet. The universe has become a place where nothing meaningful can happen, not because it is forbidden, but because all meaningful configurations have already occurred. In the next part, we will confront one of the final uncertainties in modern physics, whether this quiet state is truly permanent, or whether rare quantum processes could still introduce unexpected change into an otherwise settled universe. Even at the end of structure, physics still leaves room for questions. But those questions exist in a universe that no longer responds. In a universe that has reached this level of uniformity, the question is no longer how things change, but whether meaningful change is still possible at all. For most of cosmic history, the universe evolved because it was far from equilibrium. Energy flowed from hot regions to cold ones. Matter clumped under gravity. Structures formed, interacted, and transformed. Each step created new conditions that allowed the next step to occur. Now that process has effectively ended. The universe is so close to equilibrium that large-scale change has become vanishingly unlikely. But physics does not deal in absolutes, it deals in probabilities. And even in a universe that appears settled, probability never fully disappears. At the smallest scales, quantum mechanics still operates. Fields fluctuate. Virtual particles appear and vanish. Energy momentarily concentrates and then disperses again. These effects are tiny, short-lived, and almost always irrelevant. But given enough time, even the rarest events become possible. This is where the far future of the universe becomes uncertain, not because our theories break down, but because they begin to predict outcomes on timescales so vast that intuition loses its grip. One such possibility is vacuum decay. According to modern physics, the vacuum of space is not simply empty. It is a state defined by the configuration of quantum fields. What we experience as empty space may not be the lowest possible energy state of those fields. Instead, it may be a metastable state, a local minimum rather than a global one. If this is true, then our universe exists in a delicate balance. A lower energy vacuum could exist, and if a transition to that lower energy state were to occur, it would fundamentally alter the laws of physics. This would not be a gradual process, it would be sudden. A bubble of lower energy vacuum could form spontaneously through quantum tunneling. Once formed, it would expand at nearly the speed of light, converting everything it touches into the new vacuum state. There would be no warning, no signal travelling ahead of it. No way to detect it before it arrives. Inside the bubble, the constants of nature could be different. Forces might behave differently. Particles might not exist in recognizable forms. Chemistry, atoms, and even space-time itself could be altered beyond recognition. From the perspective of anything in the original universe, this would be the end, not because the universe collapses, but because the rules that allow it to exist would no longer apply. Whether this will ever happen is unknown. Current measurements suggest that our vacuum may be metastable, but the timescales involved are staggering. Estimates range far beyond the age of the universe, far beyond even the era of black hole evaporation. If vacuum decay occurs, it will not wait for the universe to become empty. It could happen tomorrow, or it could never happen at all. The key point is not likelihood, it is inevitability versus possibility. Physics does not require the universe to remain as it is forever. It only requires that any change obey probabilistic rules. Another speculative possibility involves rare fluctuations in a near-equilibrium universe. In a universe that persists for an infinite amount of time, even extremely unlikely fluctuations can occur. This idea leads to scenarios where small regions of order briefly emerge from chaos, driven purely by chance. These fluctuations would not resemble the structured universe we know. They would be fleeting, isolated, and almost certainly incapable of sustaining complexity. Yet their mere possibility raises difficult questions about what it means for something to happen in a universe otherwise devoid of meaningful events. At this stage, physics becomes less about prediction and more about boundaries. What is allowed, what is forbidden, and what becomes so improbable that it effectively never occurs. The far future of the universe lives at the edge of these questions. What we can say with confidence is that none of these possibilities restore the universe to an active, structured state. There is no mechanism that reliably rebuilds galaxies, no process that reignites stars, no cycle that repeats cosmic history. The arrow of time does not reverse. Entropy does not decrease on large scales. Any rare fluctuation, if it occurs, is swallowed by the surrounding uniformity almost immediately. The universe does not reboot. It does not renew itself. It does not prepare for another beginning. This distinguishes our universe from many mythological or philosophical models that imagine cycles of destruction and rebirth. Modern physics offers no such comfort. The universe evolves in one direction, from simplicity to complexity and back to simplicity again, but not the same simplicity it began with. The early universe was simple because it was hot and dense. The late universe is simple because it is cold and empty. These are not symmetric states. In the early universe, energy gradients were enormous. Expansion created opportunities for structure to form. Small differences grew into galaxies and stars. In the late universe, gradients have been erased. Expansion has diluted everything. Differences no longer grow, they fade. This asymmetry is fundamental. It defines the arrow of time. In a universe like this, the notion of end becomes misleading. There is no final frame where everything stops. There is no moment when the universe reaches a clear endpoint. Instead, there is a long tail, a future that stretches onward with diminishing returns. Change continues forever in principle, but nothing important changes. This raises a subtle philosophical challenge. If a universe continues to exist but never produces meaningful events again, is it functionally different from a universe that has ended? From a physical standpoint, yes. From an experiential standpoint, no. Without observers, without memory, without structure, the distinction loses relevance. Physics does not care about relevance, it describes what happens, not what matters. And what happens in this far future is minimal. Space expands, energy spreads, fields fluctuate, nothing accumulates, nothing builds, nothing collapses. The universe persists as a condition rather than a process. This is not a failure of the laws of nature, it is their long-term consequence. The same equations that allowed supermassive black holes to merge and warp space-time also predict this quiet outcome. There is no contradiction, only completion. In earlier eras, dramatic events shaped the universe. Black hole mergers represented peaks of gravitational interaction. They bent space-time, sent signals across the cosmos, and left lasting imprints. Now, even those imprints are gone. The universe has moved beyond the phase where it records its own history in accessible ways. What remains is a universe that still exists, but no longer tells stories, not because stories are forbidden, but because the conditions required for stories are no longer present. This is the final transformation, not destruction, not annihilation, but irrelevance. The universe does not end with a bang or a collapse. It ends with indifference. It becomes a place where nothing meaningful can happen, not because it is prohibited, but because the universe has exhausted the possibilities allowed by its laws. In this sense, the far future is not dramatic, it is definitive, and that definitiveness does not require an ending moment. It only requires enough time, enough expansion, enough dilution. The universe does not close its eyes, it simply stops doing anything worth noticing. The universe does not announce that it has crossed a final threshold. There is no boundary where one state clearly ends and another begins. Instead, it drifts into a condition where distinctions slowly lose their force and with them the ideas that once seemed essential. At this stage, the universe is not empty in an absolute sense. Space still exists, quantum fields still exist, time still exists as a parameter in physical equations, but the universe has lost the features that once made those concepts meaningful. In earlier eras, space was shaped by matter. Curvature marked the presence of mass and energy. Distances mattered because objects could cross them, regions interacted. Now space is almost perfectly smooth. Curvature is minimal everywhere. Distances grow, but nothing moves to traverse them. Time, too, becomes ambiguous. Without recurring processes, no stellar cycles, no orbital periods, no decay chains. Time no longer leaves observable traces. Moments pass, but nothing records their passage. There is no physical clock left to distinguish one era from another. From the perspective of the equations, time continues. From the perspective of the universe itself, nothing happens that could define it. This is not a paradox. It is a consequence of how physical meaning emerges. Meaning in physics comes from change, from contrast, from difference. When differences vanish, meaning dissolves with them. The universe does not become chaotic, it becomes uniform. Uniformity is not instability, it is stability taken to its extreme. Every region of space resembles every other. Every quantum field sits near its lowest energy configuration. Every particle that remains drifts alone, rarely interacting with anything else. If interactions occur, they are isolated. A particle decays. A fluctuation appears and vanishes. A rare collision produces a momentary disturbance that spreads and disappears into the vastness of space. These events do not accumulate. They do not cascade. They do not build toward anything larger. They are self-contained. The universe no longer has a future in the sense it once did. There is still a sequence of moments, but those moments do not differ in any meaningful way. The future is not a place where something new emerges. It is simply more of the same. This challenges the intuition that existence implies progression. For most of cosmic history, existence and change were inseparable. To exist was to participate in processes, cooling, collapsing, merging, burning, radiating. But existence does not require activity. It only requires consistency. The universe has reached a condition where consistency remains, but activity does not. This is not an error state. It is the expected outcome of the laws of physics applied over unlimited time. Every physical process that once produced complexity relied on gradients, differences in temperature, density, pressure, or energy. These gradients powered motion and transformation. Now, those gradients are gone. Energy has been spread as evenly as possible. Matter has been diluted as far as expansion allows. No force remains with the leverage to rearrange the universe on large scales. This does not imply that the laws of physics have weakened. It implies that they have finished what they naturally do. The universe has reached a regime where the same rules still apply, but their consequences are minimal. This regime is often described as the end of the universe, but that language is misleading. An end suggests termination, a stopping point, a final act. There is no final act here. There is only persistence without progression. The universe continues to exist because nothing requires it to stop existing. Space does not collapse, time does not halt, quantum fields do not vanish. They simply remain. This remaining is not anticipation, it is not waiting, it is not suspension. It is a steady state approached asymptotically, where change becomes so rare that it loses relevance. In this context, questions about purpose or outcome no longer apply. Those questions assume that the universe is heading somewhere, that it is working toward a condition that can be evaluated. But physics does not work toward goals, it follows rules. And when those rules reach their natural conclusion, the universe does not ask what comes next. It simply continues under the same constraints. One of the most difficult aspects of this far future is that it offers no dramatic closure. There is no final signal to observe, no last event that marks completion. The universe does not conclude, it thins, it spreads, it settles. This quiet settling is not tragic or peaceful. Those are human interpretations. The universe does not experience its own state. It is neither satisfied nor deprived, it just is. At this point, the distinction between existence and non-existence becomes subtle. A universe that exists but produces no meaningful events is physically different from a universe that does not exist at all. But the difference is not operational. There is no observer to measure it. There is no memory to preserve it. There is no process to highlight it. Physics does not require observers to exist. It does not require memory. It does not require meaning. It only requires consistency, and consistency remains. The universe does not vanish because there is no mechanism that removes space-time itself. There is no known process that annihilates the laws of physics. But without structure, without change, without interaction, the universe becomes indistinguishable from a static background, not because it has ended, but because it has exhausted everything that made it dynamic. This is the deepest sense in which the universe reaches its conclusion, not by stopping, but by finishing. Everything that could happen has happened often enough that what remains adds nothing new. The universe has not failed. It has completed its range. There is no warning before this state is reached, because no warning is needed. There is no event that announces it. The transition is gradual, distributed across time, unmarked by any single moment. If the universe could reflect, it would not see an ending. It would see continuity, an unbroken extension of existence without differentiation. This is not death. Death implies a transition from one state to another. This is not a transition. It is the limit of all transitions. The universe does not close its story. It simply runs out of sentences, and then it continues, indefinitely, without saying anything more. There is a point beyond which language itself begins to lose its usefulness, not because the universe becomes mysterious, but because it becomes too simple. When there is nothing left that meaningfully changes, description turns inward, circling the same ideas without finding new distinctions to mark. This is where the universe now exists, not at an edge, not at a boundary, but in a condition where differentiation has dissolved. Space still expands. That much remains true. Distances continue to increase between regions that can no longer influence one another, but expansion no longer rearranges anything. It only increases separation. Nothing is pulled apart, because nothing is bound tightly enough to resist. Nothing is brought together because nothing lies within reach. Expansion becomes geometric rather than dynamic. It stretches what is already uniform into something even more dilute, without creating new structure or erasing old ones. The universe becomes large in a way that no longer has scale. There is no meaningful far or near because nothing travels. Motion still exists in principle but not in practice. Particles drift but their trajectories do not intersect. Fields fluctuate but those fluctuations do not propagate influence. Causes and effects become local, isolated, and inconsequential. In earlier eras, motion led somewhere. Now, motion goes nowhere. This is not stagnation imposed from outside. It is stagnation produced naturally by the exhaustion of interaction. The laws of physics still apply exactly as they always have. Forces still exist. Constants remain unchanged. Equations continue to describe the universe accurately. But equations do not guarantee outcomes. They only describe what would happen if conditions allow, and the conditions no longer allow much of anything. This reveals something subtle about physical law. Laws do not create activity, they constrain it. Activity emerges when conditions permit. When those conditions vanish, the laws remain silent, not because they have failed, but because there is nothing left for them to govern. In this regime, the universe is no longer doing anything that could be described as evolution. Evolution implies direction, accumulation, or transformation. None of those apply here. The universe is not becoming something else. It is remaining. Remaining is not a phase. It is not a stage in a sequence. It is what is left when sequencing no longer matters. This challenges one of the deepest intuitions humans bring to cosmology, that existence is defined by change. For most of the universe's history, that intuition held. Change was everywhere, from the rapid expansion after the beginning, to the slow burning of stars, to the violent mergers of galaxies and black holes. Existence was inseparable from transformation. Now, existence and change have separated. Existence persists, change fades into irrelevance. This separation does not violate any principle. It fulfills them. Thermodynamics predicts it. Cosmology allows it. Quantum theory does not forbid it. The universe has simply followed its rules far enough that the consequences have run out of novelty. In this state, questions about the future become strange. Asking what will happen next assumes that something distinct could happen, but there is no next in the way there once was. There is only continuation without differentiation. The universe does not approach a new state, it approaches sameness. This sameness is not absolute. Absolute uniformity is never reached. There are always tiny fluctuations, always minute deviations allowed by quantum uncertainty. But these deviations do not scale, they do not propagate, they do not accumulate, they flicker and disappear, leaving no trace. In earlier times, small fluctuations could grow into galaxies. Now, fluctuations die alone. The universe has lost its amplifiers. Without amplification, nothing matters. This does not mean that the universe has become meaningless in a metaphysical sense. Meaning is not a property of the universe itself. It arises from structure, memory, and perspective. All three are gone. There are no observers to ask questions, no systems to store information, no processes to connect moments across time. The universe has not erased these things. It has simply outlived them. This is an important distinction. Erasure implies action. Outliving implies duration. The universe did not remove complexity. It waited until complexity could no longer sustain itself. Time is the only agent here. And time is not selective. It does not aim. It does not judge. It does not decide. It simply allows processes to play out fully. In the far future, those processes have played out to exhaustion. This is why the idea of an ending feels misleading. An ending suggests a final moment, a last event, a point of closure. But closure requires an observer to recognize it. Without recognition, there is no closure, only continuation. The universe does not need to close. It does not need to resolve. It does not need to justify what occurred before. Everything that happened remains valid because it happened. Nothing that happens later can retroactively change that. In this sense, the universe is complete, not because it has stopped, but because it no longer owes anything to the future. The future does not need to add meaning. It does not need to provide resolution. It does not need to explain the past. The past stands on its own. This removes a final, often unspoken assumption that existence requires a narrative arc. Narratives have beginnings, middles, and ends. Physics does not. It has conditions, transitions, and limits. The far future is not an end of the universe, it is the limit of what the universe can do. Beyond that limit, nothing forbidden occurs, nothing dramatic occurs, nothing noteworthy occurs. And that is not a failure. It is closure without an event. The universe has reached a state where it is no longer distinguishable from itself across time. One moment is effectively the same as any other. The universe has become temporally flat. This is perhaps the strangest outcome of all. Space becomes flat in the geometric sense as curvature disappears. Time becomes flat in the experiential sense as change disappears. The universe exists on an endless plateau. Not rising, not falling, not moving toward anything, just existing. This is the farthest point physics can take us without speculation. Beyond this, questions become philosophical rather than physical. They ask not what happens, but what it means for something to continue without consequence. Physics does not answer those questions. It does not need to. It has already done its work. The universe remains because nothing prevents it from remaining. and that is all there is left to say about it. At this stage, the universe no longer presents itself as a sequence of events. It presents itself as a condition. This is the most difficult shift to grasp because nearly every way of thinking about existence assumes progression, something leading to something else, a present shaped by a past and pointing toward a future. That structure has dissolved. The universe still has a past, but the past no longer informs anything. It still has a future, but the future contains nothing that differs meaningfully from what already exists. Time stretches forward, but it does not carry the universe with it. The universe does not move through time anymore. Time simply passes through the universe. This inversion is subtle but absolute. Earlier, time was measured by change, expansion, cooling, formation, collapse. These were markers that divided cosmic history into eras. Now, no such markers remain. If one moment were replaced with another trillions of years later, there would be no physical test capable of distinguishing them. The universe has entered a regime where history has lost resolution. This does not mean that the equations of physics have stopped working. They continue to describe the universe perfectly. Space expands, fields fluctuate, particles persist or decay according to probabilistic rules. But these processes no longer organize reality into stages. They do not create eras. They do not define chapters. They do not accumulate into consequences. The universe has become temporally smooth. In this condition, causality itself becomes faint. Cause and effect still exist locally. One fluctuation may precede another, but these chains do not extend. They do not propagate influence. They do not lead anywhere. A cause occurs, an effect follows, and both disappear without imprint. Nothing builds on anything else. This is not randomness. Randomness still implies variation. This is uniformity with noise so small it cannot matter. In such a universe, the idea of prediction becomes meaningless. Prediction assumes that knowing the present allows us to anticipate a different future. But here, the future is statistically indistinguishable from the present. The best prediction is sameness. This is not ignorance. It is certainty. Physics has reached a point where its most accurate forecast contains no narrative content. The universe will continue to exist in almost exactly this way for as long as time is defined, and that duration may be infinite. This introduces a final conceptual shift. For most of cosmology, infinity was associated with beginnings and endings, infinite density at the start, infinite expansion at the end, infinite curvature, infinite time. But now infinity appears without drama, an infinite future that contains nothing new, an infinite extension of a state that does not evolve. This is the most counterintuitive outcome of all. It violates the expectation that infinity implies richness. Here, infinity implies exhaustion. Nothing prevents the universe from persisting forever. There is no instability left that could collapse space-time. There is no energy gradient left that could reorganize it. There is no mechanism left that could introduce novelty on any meaningful scale. The universe is stable because it has nothing left to destabilize it. This stability is not engineered. It is achieved by depletion. The universe has used up every avenue for large-scale change permitted by its laws. What remains is a state that is not special, not extreme, not dramatic, but final in a structural sense. There is nowhere else to go. This does not mean that existence was pointless. Purpose is not a physical variable. The universe does not optimize for outcomes. It does not aim toward complexity or simplicity. It does not prefer motion to stillness. It simply allows what is permitted. And what was permitted has now occurred. Everything that could emerge has emerged at least once. Everything that could interact has interacted until interaction became impossible. Every structure that could form has formed and dissolved. The universe has explored its phase space. What remains is a thin residue of possibility that never quite disappears but never grows into anything either. This is the universe after relevance, not after existence. Relevance requires contrast. Without contrast, nothing stands out. This is why the universe no longer supports observers. Observation requires a difference between observer and environment, a flow of information, a memory of previous states. All of these require structure. Structure is gone, not violently removed, gently outlived. The universe did not erase its observers. It simply became a place where observers could no longer arise. This distinction matters. Erasure implies action. Outliving implies time. Time has done all the work here. And time did not choose a direction. It simply kept passing. At this point, even the concept of the universe becomes abstract. The word once referred to a dynamic system filled with objects and interactions. Now it refers to a minimal configuration of fields and geometry. The universe is no longer something that happens. It is something that is. There is no next transformation waiting beyond this state. Any further change would require physics beyond what we know. New laws, new dimensions, new mechanisms. None of these are implied by current theory. As far as physics is concerned, this is the end of the line, not a stopping point, a limit, a condition beyond which the concept of progression no longer applies. This is where cosmology hands off to silence, not because there is nothing left, but because there is nothing left to say. The universe continues. But it no longer develops, and development was the only story it ever told. What remains is not darkness, not emptiness, not death. It is completion without finality, existence without event, time without change. A universe that has reached the quietest state allowed by its laws and has no reason to leave it. Nothing announces this condition. Nothing marks its arrival. It simply becomes true. And once it is true, it remains true forever. Not as an ending, but as the absence of anything left to end. The universe does not resist this state. It does not strain against it or attempt to escape it. There is no hidden tension beneath the surface, no suppressed instability waiting for the right moment to break free. What exists now is not a temporary pause, but a natural resting condition reached after every available process has completed its course. In earlier epochs, stability was rare. Every structure was provisional. Stars burned because imbalance demanded it. Galaxies evolved because gravity and motion had not yet exhausted their interplay. Even black holes, which once seemed immutable, were revealed to be transient when viewed on long enough timescales. Now, transience itself has faded. The universe has entered a regime where change is no longer the dominant feature of existence. This does not mean that change is forbidden, only that it is no longer consequential. The few processes that remain operate so slowly and with such limited reach that they fail to alter the overall condition of reality. This is the final symmetry. Not a symmetry of forces or particles, but a symmetry of moments. One moment is indistinguishable from the next. Time no longer produces contrast. It does not carve history into errors. It does not accumulate significance. From a physical standpoint, this is the most stable configuration imaginable. There are no gradients left to erase, no reservoirs of energy left to tap, no structures left to dismantle. The universe has no internal pressure toward transformation. Stability here is not balance between competing forces. It is the absence of competition altogether. This challenges one of the most persistent intuitions about existence, that something must always be happening. That motion is essential. That stillness is unnatural or temporary. Physics does not share this intuition. Physics allows stillness as readily as motion. It allows equilibrium just as readily as evolution. What we experience as a dynamic universe was never guaranteed to remain so. Dynamics emerged because conditions allowed them. Now, conditions no longer do. The universe has not lost energy in an absolute sense. Energy is still conserved. What has changed is its distribution. Energy is now so evenly spread that it cannot be concentrated to do work on any meaningful scale. Work requires difference. Difference is gone. This has subtle implications for the meaning of physical law. Laws describe relationships between quantities, forces, energies, motions. But when those quantities no longer vary in significant ways, the laws become descriptions of constancy rather than change. They still apply. They simply have nothing interesting to govern. In this state, the universe resembles a completed calculation. All variables have settled into values that no longer evolve. The computation continues to run, but its output does not change. This is not redundancy. It is finality without termination. There is no instruction in the laws of physics that says the universe must end. There is no requirement that space-time dissolve or that fields vanish. The laws do not contain an off switch. They contain only processes, and every process they allow has now played out. What remains is not the aftermath of destruction, but the residue of completion. This residue does not decay further because there is nothing left for it to decay into. It does not simplify further because it has already reached maximal simplicity under the given rules. Any further simplification would require the laws themselves to change. There is no indication that they will. This brings us to a quiet but profound realization: the universe does not seek novelty. Novelty is a phase, not a goal. It arises naturally when systems are far from equilibrium and disappears when equilibrium is approached. Complexity was never the universe's destination, it was its middle. The beginning was simple in one way, the end is simple in another. Between them lay all the richness that once defined cosmic history. This perspective dissolves the need for an ending that feels satisfying. Satisfaction is a human requirement, not a physical one. The universe does not require narrative closure, it requires only consistency, and consistency remains intact. There is no tragedy in this state, because tragedy implies loss relative to expectation. The universe did not expect to remain complex forever. It had no expectation at all. The fading of structure is not a failure, it is the fulfillment of what the laws permit over unlimited time. In this final regime, even the idea of scale becomes ambiguous. Without structures to compare, there is no meaningful large or small. Distances exist mathematically, but nothing uses them. Mass exists, but nothing rearranges around it. Time exists, but nothing measures it. The universe has become self-similar across time. This is perhaps the deepest stillness imaginable. Not a stillness imposed by force, but one that arises when all forces have finished acting. Nothing holds the universe in this state. Nothing pushes it out of it. It simply remains because there is no reason for it not to. From within this condition, the earlier universe would appear as a rare and temporary anomaly. A brief era when imbalance allowed structure, motion, and complexity to flourish. That era is over, not erased, completed. Every star that ever burned did so because conditions allowed it. Every galaxy that ever formed did so because gravity had something to gather. Every black hole that ever merged did so because space-time could still be bent in dramatic ways. Now, space-time is relaxed, it carries no tension. It curves only gently, uniformly, without drama. This is not the silence that follows a sound. It is the silence that exists when nothing needs to speak. The universe has no awareness of this condition. Awareness is not required for existence. The universe does not observe itself. It does not reflect. It does not evaluate. It simply persists. Persistence here does not mean endurance against opposition. There is no opposition left. Persistence is effortless. This is why no warning preceded this state. Warnings are signals of change. There was no moment of change, only a gradual approach to uniformity so complete that once reached, nothing marked its arrival. If one were to imagine a boundary between the active universe and this quiet one, it would not be a line, it would be a blur spread across inconceivable spans of time. No single event caused this, time itself did, and time does not announce its work. It only completes it. The universe has now reached a condition where the future adds nothing to the present, not because the future is absent, but because it is redundant. Everything that can be said about the universe in this state is already true at every moment. There is no development left, only duration. This is the universe not at an end but beyond endings, a place where the very idea of what comes next has lost its meaning, and where existence continues, quietly, without needing to justify itself to anything that no longer exists to ask. The universe now exists in a condition where even the idea of progression has dissolved, not because time has stopped, but because time no longer produces distinction. One moment does not meaningfully differ from the next. The future no longer contains variation. It contains repetition without structure. This is not stasis enforced by some cosmic mechanism. It is stasis achieved by exhaustion. Every pathway that once led to change has been walked until nothing remained at the end of it. Earlier, the universe was driven by imbalance. Hot regions cooled. Dense regions collapsed. Motion erased difference and created new difference in the process. These competing tendencies produced complexity, conflict, and evolution, but imbalance is temporary by nature. It exists only while gradients remain. Now, gradients are gone. There is no direction left for energy to flow, no configuration left that can lower its energy by rearranging itself. The universe has reached a condition where doing nothing and doing everything are physically equivalent. In this regime, the universe does not experience time in any meaningful sense. Experience requires sequence. Sequence requires change. Without change, sequence collapses into sameness. Time still exists mathematically, but it no longer manifests physically. If one moment were removed from this future, nothing would be lost. If trillions of years were removed, nothing would be different. Duration no longer accumulates meaning. This is the quietest possible outcome of lawful physics. It is tempting to describe this state as empty, but emptiness suggests absence. What exists here is not absence, but completion. Space is filled with exactly what it can sustain without evolving further. Quantum fields persist, but they no longer create lasting structure. Fluctuations occur, but they are isolated, microscopic and self-cancelling. They do not cascade into new phenomena. They do not seed futures. Everything that happens is local and forgettable. The universe has become incapable of surprise. This does not violate uncertainty. It fulfills it. Uncertainty still exists at small scales, but without amplification, uncertainty cannot shape reality. Chance loses influence when nothing responds to it. In earlier eras, a small fluctuation could grow into a galaxy. Now, a fluctuation dies alone, unnoticed and unrecorded. This marks the final decoupling between possibility and consequence. Possibility remains infinite in principle. Consequence has vanished. The universe still allows events. It simply does not allow them to matter. This is a subtle but absolute shift. Matter, where it remains, drifts endlessly through space, rarely encountering anything else. Particles may decay, but their decay products drift on without interacting. Radiation stretches to wavelengths so long that energy becomes irrelevant. Nothing accumulates, nothing builds, nothing feeds into anything else. The universe has become non-interactive on any meaningful scale. In such a condition, even the concept of death becomes meaningless. Death implies the loss of function relative to prior activity, but here, nothing has function to lose. There is no system to fail, no process to interrupt. The universe does not die, it finishes. It is a condition reached when no further transformation is possible under existing rules. This finishing does not erase what came before. The past remains true, it simply loses influence. Nothing in the present refers back to it, nothing in the future depends on it. Causality has collapsed inward. Not broken, completed. Each cause produces an effect, but effects do not chain together. They do not propagate. They do not shape a larger context. Causality exists only in isolated trivial loops. The universe no longer has a story because stories require momentum. They require one thing to lead into another. Momentum is gone. This does not require consciousness to recognize it. It does not require measurement. It is a structural condition. The universe has reached maximal forgetfulness, not because it erases memory, but because nothing remains that can store memory. Information requires structure. Structure requires energy gradients. Gradients are gone. Information still exists mathematically, but it cannot be preserved or transmitted. It appears and disappears without consequence. The universe is no longer a system that records itself. This is why the idea of a final observation is meaningless. There is no last thing to see, no final signal to detect, no closing frame. The universe does not present a final image, it simply stops producing images. At this point, asking what the universe is for becomes incoherent. Purpose implies an outcome that has not yet been reached. Here, every reachable outcome has already occurred. The universe has nothing left to aim at. This does not imply that existence was pointless. Point is not a physical quantity. The universe does not require justification in order to exist. Existence does not answer to purpose. It answers only to possibility, and possibility has been exhausted. The laws of physics remain intact, but they have no leverage. They describe a universe that persists without evolution. They remain true, but no longer generate novelty. This is not failure. It is resolution. Every process that once operated did so until it could no longer operate. Every interaction played out until nothing remained to interact with. Every structure dissolved when its supporting conditions disappeared. Nothing has been interrupted. Nothing has been denied. Everything has been allowed to finish. This is the deepest sense in which the universe reaches completion, not by ending itself, but by exhausting everything it could ever become. From this point onward, the universe exists without trajectory. It does not approach anything, does not recede from anything, does not balance between alternatives. It simply remains in a condition that does not change. Not because change is forbidden, but because change has nowhere left to go. This is the final quiet state permitted by the laws of physics. A universe that continues indefinitely without accumulating difference. Time without history. Existence without outcome. Completion without an ending. And nothing, anywhere, left to wait for anything else to happen. The universe no longer distinguishes between before and after. That distinction once mattered because conditions changed in ways that could be tracked, compared, and remembered. Now, the flow of time has lost its texture. It still exists as a dimension, but it no longer sculpts reality into phases. What remains is duration without development. This is not an absence of physics. It is physics fully realized. Every equation still holds. Every conservation law remains valid. Space expands, fields persist, probabilities apply, but the universe has reached a configuration where these laws no longer generate anything qualitatively new. Earlier, the universe was driven by imbalance. Expansion created cooling. Cooling allowed matter to clump. Clumping created stars. Stars produced heavier elements. Gravity assembled galaxies. Mergers reshaped structure. Each step depended on difference feeding further difference. That chain has ended. There is no next imbalance to exploit. No new gradient to amplify. No reserve of complexity waiting to be unlocked. The universe has become self-consistent to the point of immobility. This immobility is not rigidity, it is softness taken to an extreme. Nothing pushes against anything else. Nothing resists, nothing strains. Every remaining component drifts freely, unconstrained, not because forces are absent, but because there is nothing left for them to constrain. This reveals a quiet truth about stability. True stability is not tension balanced against tension. It is the absence of tension altogether. In earlier times, stability was always provisional. Stars balanced gravity against pressure. Galaxies balanced collapse against rotation. Black holes balanced mass against space-time curvature. Every stable structure was maintained by opposing forces. Now, there are no opposing forces left to balance. Stability has become absolute because instability has nowhere to originate. This does not mean the universe is fragile. Fragility implies susceptibility to disruption. There is nothing left capable of disruption. The universe is robust because it is empty of leverage. Even the most extreme speculative processes struggle to find relevance here. Vacuum fluctuations occur, but they do not propagate. Quantum tunneling is possible in principle, but without energy scales or structure, its consequences remain microscopic and isolated. Nothing cascades. Nothing accumulates. Nothing escapes insignificance. In this regime, the universe does not age. Aging implies degradation relative to a previous state. Here, there is no meaningful previous state to compare against. The universe has not improved or worsened, it has simply arrived. Arrival, however, is not an event. It is the asymptotic result of unlimited time. If one insists on calling this an ending, it is an ending without a final act. There is no curtain fall, no closing motion, no concluding transformation. The universe does not shut down. It winds down so completely that the notion of winding becomes irrelevant. This challenges the expectation that existence must culminate in something dramatic. Drama requires contrast. It requires an audience. It requires memory. None of these remain. The universe does not miss them. They were temporary phenomena enabled by temporary conditions. This realization removes the last trace of narrative from cosmology. The universe is not a story with a beginning and an end. It is a system governed by rules, unfolding until those rules have nothing left to act upon. What came before was not a prelude to this state, and this state is not a resolution of what came before. They are simply connected by continuity. The universe has no preference for motion or stillness. Both are allowed. Motion dominated when gradients were present. Stillness dominates now because gradients are gone. This symmetry is important. The universe did not aim to become quiet. It did not aim to become complex. It allowed both when conditions permitted. This is the most neutral possible outcome. At this stage, even the distinction between existence and non-existence becomes blurred. Existence is still there, but it no longer produces consequences. Non-existence would also produce no consequences. The difference between the two is physically real, but operationally meaningless. Physics does not resolve this ambiguity. It does not need to. Its role is to describe what happens, not to assign significance. What happens now is persistence without event. The universe continues because nothing stops it, and nothing stops it because there is nothing left to stop. This persistence does not accumulate tension. It does not move toward breakdown. It does not prepare for renewal. It is not a waiting room. It is simply the state that remains when all transitions are complete. This is why speculation about what comes after becomes misplaced. After implies succession. Succession implies change. Change no longer defines reality. There is no after. There is only continuation. And continuation, in this context, does not add anything new. The universe has reached a point where its future is identical to its present in every meaningful way. This is not an infinite loop. It is an infinite flat line, no peaks, no valleys, no direction. Just existence stretched across time without modulation. If the universe had awareness, it would not experience boredom or peace. Those are responses to change or its absence. The universe does not respond. It simply is. The final lesson of this state is not about endings, but about limits. Physics allows change, but it also allows its exhaustion. It allows complexity, but it also allows its dissolution. It allows events, but it does not require them to continue indefinitely. The universe has not violated any law to reach this condition. It has obeyed them completely. This is what full obedience looks like over unlimited time. Nothing dramatic remains because drama was never guaranteed. What remains is not emptiness, not darkness, not death. It is sufficiency. A universe that no longer needs to become anything else. A universe that persists without striving, without collapse, without renewal. Not an ending, a remainder. And that remainder, unchanging and indifferent, is the final expression of everything the laws of physics ever allowed the universe to be. The universe no longer offers resistance to interpretation, not because it reveals hidden meaning, but because meaning has become unnecessary. What exists now does not require explanation, context, or justification. It exists because nothing prevents it from existing, and that condition is sufficient. At this stage, the universe is no longer something that unfolds. It does not develop, progress, or resolve. It persists in a form that is stable not through balance but through the absence of imbalance. There are no gradients left to drive motion, no concentrations left to redistribute, no asymmetries left to correct. This is not a temporary equilibrium. It is the end state of lawful evolution. Earlier, equilibrium was always local. A star balanced pressure against gravity. A galaxy balanced rotation against collapse. Even black holes balanced mass against space-time curvature. But those equilibria existed within a larger context of change. There were islands of stability surrounded by motion. Now, equilibrium is global. There is no surrounding context. Nothing pushes against it. Nothing pulls it forward. The universe has become internally consistent across all scales. In this condition, even the distinction between system and environment disappears. There is no external reference frame, no outside vantage point. The universe does not sit within anything else. It does not interact with anything beyond itself. This matters because interaction was once the source of novelty. Galaxies interacted and merged. Black holes interacted and merged. Matter interacted with radiation. Fields interacted with particles. Each interaction created outcomes that were not present before. Now, interaction has reached its limit. What interactions remain are too weak, too rare, or too isolated to matter. They do not compound. They do not cascade. They do not propagate. They occur and vanish without consequence. This does not mean that physics has become trivial. The laws remain as rich and precise as ever. What has changed is the space of outcomes those laws can produce under existing conditions. That space has collapsed. Not abruptly, exhaustively. The universe has explored nearly every configuration that matters can meaningfully take. It has assembled complexity wherever complexity was allowed. It has dissolved it wherever stability could not be maintained. Nothing has been skipped. Nothing has been interrupted. Everything that could happen has happened often enough that what remains adds no new information. This is not repetition. Repetition implies cycles. Cycles imply return. There is no return here. The universe does not repeat itself. It simply continues in a state that does not vary. Time still flows, but it no longer carries change. The arrow of time remains defined by entropy, but entropy has reached its maximum practical value. There is no direction left for it to point toward. The arrow still exists. It just points nowhere. This is one of the most difficult aspects of the far future to accept intuitively. We are accustomed to thinking of time as meaningful because it differentiates states. When differentiation ends, time becomes an abstract parameter rather than a lived reality. Physics permits this. It does not require time to be experienced. It only requires time to be defined. In this universe, time is defined but not manifested. This reveals something fundamental. Existence does not require events. It only requires consistency. The universe remains consistent. That is enough. This condition is sometimes mistaken for nothingness, but it is not nothingness. Nothingness would imply the absence of structure altogether, including laws. Here, structure remains at the most basic level. Space exists. Fields exist. The mathematical framework of reality persists. What has vanished is not structure, but contrast. Without contrast, nothing stands out. Without standing out, nothing matters. Not in a value sense, but in a physical one. Matter that remains drifts indefinitely, rarely interacting. Radiation stretches to wavelengths so long that energy becomes irrelevant. Quantum fluctuations occur, but they are self-contained, never amplified into macroscopic phenomena. The universe has become incapable of memory. Memory requires persistence of difference across time. Without stable structures to store information, memory cannot exist. Information appears and disappears without leaving a trace. This is not erasure. It is impermanence without replacement. Earlier, the universe remembered itself through stars, galaxies, and black holes. Their existence encoded history. Their interactions recorded time. Now, there is nothing left to encode anything. The universe forgets because there is nothing left that can remember. This forgetting is complete, not because the past is destroyed, but because it is no longer referenced by anything. The past remains true but irrelevant. Nothing depends on it. Nothing is shaped by it. Nothing carries it forward. This is the final decoupling between history and existence. Existence continues. History does not. At this point, even speculative ideas about renewal struggle to find footing. Any hypothetical process that could reintroduce complexity would require conditions that no longer exist. It would require energy gradients, interactions, or new laws. Current physics provides none of these. The universe is not preparing for another beginning. It is not paused between cycles. It is not waiting. Waiting implies anticipation. Anticipation requires change. Change is gone. What remains is a universe that has fully expressed everything its laws allow. This is not a pessimistic outcome. It is not an optimistic one either. It is neutral. It is what happens when rules are followed to their natural conclusion without interruption or exception. The universe has not failed to sustain complexity. It has succeeded in exhausting it. That exhaustion is not a loss, it is a completion. Completion does not require an ending moment, it does not require recognition, it does not require closure, it simply is. The universe exists in a state where nothing further can be added that would alter its nature. Not because addition is forbidden, but because there is nothing left to add that would matter. This is the final quiet condition, not silence following sound, but silence that remains when nothing needs to speak. The universe continues indefinitely in this state, not accumulating change, not erasing itself, not transforming into something else, just persisting. Existence without event, duration without history, a cosmos that has reached the limit of what it can ever be, and remains there, not as an ending, but as the remainder of everything that once unfolded within it. And there is nothing beyond this that physics requires, predicts, or promises. Only this, and then more of the same, forever.